All right, welcome everyone to today's seminar. Today I'm happy to have Dr. Murong Qin. Dr. Qin did her undergrad and master's at Shandong University. In 2020, she received her PhD from Dartmouth, studying the role of emic waves in relativistic electron precipitation. Following her PhD, she joined Dr. Wenli's research group at the University of Boston University, and has continued to research energetic electron precipitation at low Earth orbit. Today, I'm happy to have Murong here to speak with us about characteristics of precipitation observed by the electron losses in fields investigation, or the ELFIN CubeSat. With that, if you'd like to take it away.
Oh, thanks, Kyle, for having me here, and thanks everyone for attending. So today I'm going to talk about the energetic electron precipitation at low Earth orbit. And I know this topic has been covered in many previous seminars, like those given by Wichao and Lauren. So today I would like to just focus on some statistical characteristics of the energetic electron precipitation from ELFIN's perspective. And before that, I would like to thank my collaborators here at BU, and also like Richard Selaznik, who just retired from the Air Force Research Laboratory, and of course the ELFIN team in UCLA. So first I will start with some background about the energetic electron precipitation mechanisms. So there are many mechanisms that can drive energetic electron precipitation. One of them is a wave-particle interaction, that when a particle senses a wave with its frequency Doppler shifted to the particle's gyro frequency or its harmonics, it can interact strongly with the waves and either getting accelerated or being precipitated into the loss cone. And here, this plot here shows you the spatial distribution of various plasma waves on a global scale. We can see that the Wismode heat waves are confined to this region with cold plasma, and this region can extend it down to the magnetopause during enhanced convection, which is called the plasmaspheric plumes. And electrons from the tail can excited chorus waves on the downside during enhanced convection, and also emic waves can be excited by the ions transported from the tail on the dusk side. And there are also other waves can cause electron precipitation through pitch angle scattering, like the electrons cyclotron waves or time domain structures. But these are known to be mainly responsible for precipitating electrons below a few keV. So here we just focus on the electron precipitation driven by emic waves and Wismode chorus and heat waves. So Wismode waves are right-hand polarized waves, and there are various types of Wismode waves, including the chorus wave and heat waves. Here, the upper left panel here shows you an example of heat waves, which you can see that it's broadband incoherent waves. And the lower panel shows an example of chorus waves. You can see it could occur in two bands, whereas the lower band usually have frequencies from 0.1 to 0.5 electron gyro frequency. And the upper band usually have frequency between the 0.5 to 0.8 electron gyro frequency. And for the right plot here shows the global distribution of the chorus waves by semis. You can see that during enhanced geomagnetic activity, the Wismode wave amplitude are also increased, and the enhanced region just moves closer to the Earth during enhanced geomagnetic activities. And if you look at the chorus waves on the dusk side, you can see on the midnight, you can see that the midnight chorus waves occur only below L shell of 8. Wismode chorus and heat waves can precipitate electrons from tens of keV to 1 MeV. They can generate the diffusive and pulsating aurora, and large amplitude oblique Wise-mode waves have also been shown to cause superfast electron precipitation from nonlinear Landau trapping. So here, the left plot shows an example of electron precipitation observed through the barrel X-ray count rate associated with the Wise-mode chorus and His waves observed by Van Allen probes. Here, the upper two panels show the conjunction between barrel and Van Allen probe, and the following is the Wise-mode wave power spectral density. And panel D here shows the diffusion coefficients near the loss cone that is caused by the observed Wise-mode waves. You can see that the diffusion coefficients just decrease as energy increases for electrons above tens of keV. This indicating that Wise-mode waves are more efficient at precipitating tens to hundreds of keV electrons than the MeV electrons. And the last panel here shows the X-ray count rate generated by the electron precipitation, where you can see the modulation in the X-rays shows almost apple-to-apple correspondence with the Wise-mode wave amplitude and the diffusion coefficients. And Wise-mode waves can also drive microburst, which is a kind of impulsive rapid precipitation on a time scale of subseconds. Here is work shown and done by Brandman 2017, where the upper panels shows the chorus elements observed by Van Allen probes, and the lower panel shows the microburst observed by Firebird. And this work proved the connection between the chorus elements and the microburst. The next is the EMIC waves. So EMIC waves are narrow-banded left-hand polarized electromagnetic waves that are usually generated by the equator, and they typically have a frequency range between 0.1 to 5 Hertz in observation, and they are usually generated by the recurrent temperature anisotropy during magnetic storms or substorms, or the daytime magnetic field compression. And in a multi-ion plasma species, EMIC waves can be excited in three distinctive bands: the hydrogen band between the hydrogen frequency and helium frequency, and also the helium band between helium frequency and also the oxygen frequency, and also the oxygen band EMIC wave, which is not shown here. Here, the right plot shows you the global distribution of the occurrence probability of hydrogen band and helium band EMIC waves. And this observation is from Themis, and you see they are at L shell greater than 6. You could see from this figure that the downside EMIC waves tend to lie in the hydrogen band at a higher L shells greater than 10, and the dusk side EMIC waves tend to occur most often in the helium band. And this slide shows you the EMIC wave distribution at lower L shell from Van Allen probes. During this quiet times, you can see that the hydrogen band and the helium band EMIC waves they occur almost evenly across all L shell and MLT. But as the geomagnetic activity getting enhanced, both hydrogen band and helium band EMIC waves tend to occur on the dusk side, and the active enhanced wave activity region moves closer to the Earth as the geomagnetic activity increases. The EMIC waves have been known to be efficient for precipitating MeV energy electrons, and so producing the fast loss of radiation-bound electrons. Here, the left plot shows an example of relativistic electron precipitation observed by the calorimetric electron telescope associated with the hydrogen band, helium band EMIC waves observed by Van Allen probes. So EMIC waves have also been shown to be able to precipitate relativistic microburst, which is shown in the case in Shrimko's 2022 paper, where the upper panel here shows a ground-based magnetometer observation of EMIC waves. And the lower panel shows the microburst observed by SAMPAX. Recent theoretical and observational studies also show that EMIC waves can drive precipitation down to sub-MeV energy range. So this is showing you the statistical results of the peak energy of the EMIC-driven precipitation from poles, where you can see that the dominant population of those EMIC-driven events have peak energy around 200 to 500 keV, and there's a secondary peak with occurring with the peak energy in the 0.8 to 4 MeV. And there are several scenarios being proposed to explain those sub-MeV electron precipitation, such as non-resonant interactions by Xin An and also Lunjing Chen, and also the nonlinear fractional interaction being proposed recently, and it could also be explained by the wave frequency close to the ion frequency, and also the high ratio of plasma frequencies to gyro frequency. Angelic electron precipitation can also be driven by current sheet scattering, which is caused by the violation of the first adiabatic invariant. So when the electron cyclotron radius approaches the curvature radius of the magnetic field line. And so this is a typical example of electron precipitation driven by current sheet scattering, where when the trapped flux, which the solid, which dashed line is close to the precipitating flux, which is represented as a solid line. And those boundaries are called as the isotropic boundary. At the poleward region of the isotropic boundary, the trapped flux are almost equals to the precipitating flux. Since the pitch angle is isotropic in this region, so here is called the isotropic boundary. And you can see that as the curvature radius is smaller at higher IL shells, so the precipitation at lower energies can occur at higher IL shells, but higher energy precipitation occurs at lower IL shells. Given this complex precipitation mechanisms and distinctive features of each kind of precipitation, so it's crucial to investigate the general properties of electron precipitation at LEO. And the global precipitation of electron precipitation has been investigated for decades. For example, this is the global distribution of the great density keV electron precipitation flux, which was investigated by Lam 2010. This precipitation flux is found to be enhanced from midnight to noon sector, and this is consistent with mode chorus wave driven precipitation. And the global distribution of electron precipitation at relativistic energy range has also been investigated. This is an example shown in Lauren Blum's 2015 paper, where they're using SAMPAX observation and found that the MEV electron precipitation band occurs primarily from the dusk to midnight sector. But the greater than 1 MeV microburst mainly occur from midnight to the noon sector. And this indicates that there might be different drivers for those two types of precipitation. There have also been studies on the energy spectrum of the electron precipitation. Here, the upper left panel shows the occurrence rate of the relativistic electron precipitation with a folding energy less than 0.2 MeV using SAMPAX measurement. These are called softer events. You can see that their occurrence is highest from midnight to afternoon sector. And the right panel here shows the relativistic electron precipitation with E folding energy greater than 0.5 MeV. And these are called the hard events, and they mainly occur from the dusk to midnight sector. The lower panels shows observations from pulse measurement, where the left panel here corresponding to the soft events with the ratio of flux in E3 N channel to P6 N channel greater than 50 and less than 100. So you can see their distribution is quite similar to those observed by SAMPAX. But for the hard events with the ratio less than 5, they occur both on the midnight and also the day side. And the generation mechanism is still needed to be further investigated. So despite all those efforts in understanding the electron precipitation at LEO, more accurate estimation of electron precipitation at the low Earth orbit is still needed to quantify the radiation belt electron loss and also the energy input into the atmosphere, and also the global behavior of the energy spectrum and pitch angle distributions of the energetic electron precipitations are still needed to provide more comprehensive insights into the dominant drivers at various locations. So what we are going to use in this work is the pitch angle and energy resolved measurement from ELFIN CubeSats. So the ELFIN CubeSats were launched in 2018 in a nearly circular orbit at an altitude about 450 kilometers. And it has an orbital period about 90 minutes with an inclination about 93 degrees. And the electron head on the energetic particle detector can measure electrons with from 50 keV to about 5 MeV, and with an energy resolution about 40%. And it has a spin period of 3 seconds, and each spin can be divided into 16 or 32 sectors. This allows for pitch angle and energy resolved measurement of electrons, which means we can dig deeper into the behavior of energetic electron precipitation and understand the potential drivers of the precipitation. And here we have a couple of examples of ELFIN measurement. Moving from top to bottom, we have the trapped energy flux followed by the precipitating flux, and then the precipitating to trapped ratio. And next two panels shows the backscattered flux and backscattered to trapped ratio. And the last two panels here shows the pitch angle distribution for these two example energy channels. And if you check the precipitation ratio, we got the 3 intervals marked with the colored bars. During the first time interval, you can see the precipitation mainly occurs at energies above 200 keV, and the precipitation ratio increases as energy increases. And this is typically driven by EMIC waves. And during the second time interval, the precipitation is mainly below 400 keV, and the precipitation ratio just decreases as energy increases. This could be potentially driven by Wisdom mode chorus or heat waves. And for the third time interval, the precipitation ratio is close to 1 with an energy dispersion in L shell. And this behavior is typically associated with current shape scattering. So using the data from 2019 to 2022, we performed a statistical study of electron precipitation. And this slide here shows you the global distribution of the 60 keV electrons, which we take the median value in each bin. So going from top to bottom, we've got the trapped energy flux, the precipitating energy flux, and the precipitation to trapped ratio. And moving from left to right, we got the different geomagnetic activities. And as the geomagnetic activity increases, both the energy flux and the ratios all showed enhancement. And now if you compare the precipitation energy flux with the precipitation ratio, you can see that their distributions are quite different. The energy flux of the precipitation during active conditions reaches its peak around the dawn to noon sector, but the precipitation ratio is highest around midnight. If you compare the distribution of the precipitation ratio with the distribution of chorus waves, you can see that the distribution from the dawn to noon sector are quite similar. But on the night side, the precipitation ratio might be affected by a combination of both current shade scattering and chorus waves, although further analysis is still needed to determine their relative roles. And it's worth noting that because the chorus wave is only confined to region of L shell less than 8, so the precipitation between L shell from 8 to 10 are likely mainly driven by current shade scattering. So this plot here further shows the distribution of electron precipitation driven by with mode waves from ELFIN. Those with mode wave driven electron precipitation are sorted by the precipitation ratios at around 60 keV. So you can see that the small ratio events with precipitation ratio between 0.1 to 0.2, they occur quite evenly across all L shell and MLT sectors, with an occurrence rate about 20 to 40%. This suggests that both chorus and heat waves may drive these small ratio events. And for the events with ratio from 0.2 to 0.4, the occurrence rate decreases to 5% to 15%, with a preferential occurrence at L shell greater than 4, and a peak in the afternoon sector. And this peak could be potentially caused by the plume haze, which frequently occurs in the afternoon sector. And this is not been seen in our previous slide about the statistical distributions. This is because the previous slide shows the median value, which may be dominated by the background values with small ratios. So this feature is not seen there. And for the events with higher precipitation ratios from 0.4 to 0.7, the higher occurrence rate tend to occur at L shell greater than 5, and from the midnight to afternoon sector with a gap near noon. So this indicates that those precipitation might be driven by both chorus waves from midnight to dawn sector and also plume haze in the afternoon sector. For those precipitation events with precipitation ratio greater than 0.7, those events are mostly concentrated in the midnight to noon sector at large L shells with a peak occurrence of only about 5%. And then this slide shows you the precipitation and the backscattered flux. So you can see that the backscattered flux also increases with enhanced geomagnetic activity. And during weak precipitation, the backscattered energy flux is comparable to the precipitation energy flux. However, in the regions with enhanced precipitation, only 10 to 20% of the precipitation electrons are backscattered. And this is consistent with the results in Bob Marshall's 2018 work, where you can see there's only about 10 to 20% of fraction of particles being backscattered. This is probably because as the precipitation ratio increases, more electrons are deep into the loss cone and tend to be backscattered less. And here is showing you the global distribution of the 1 MeV electrons. And here we take the 75th percentile value in each bin. And again, we see that the precipitation ratio is different from the precipitating energy flux. For the precipitation ratio, one point you could notice that is the precipitation ratio is pretty low on the day side. Another point is that the precipitation ratio noticeably increases near the dusk sector during the enhanced geomagnetic activity, which might be related to the enhanced emic wave driven precipitation. For the backscattering ratio, we can see that it keeps low during all the geomagnetic conditions. This might be because the higher energy electrons penetrate to lower altitudes in the atmosphere, so they will have a lower chance of being backscattered. And this is further showing you the distribution of electron precipitation driven by emic waves. This work is led by Dr. Luisa Campagnolo in our group, where you can see that the emic wave driven precipitation mainly occurs from the dusk side to midnight at around L shell from 4 to 7. But it was noting that for this work, the electron emic driven precipitations are selected when there is post observation of proton precipitation as a proxy. So not all the emic wave driven events are included here. Instead, Vasilis' 2023 paper, they've included all the emic wave driven events by the end of 2021, where you see in addition to this precipitation at lower L shells, there's a second class of emic wave driven precipitation at L shell from 8 to 12 around the midnight and down sector. So this means that the emic waves can contribute to both the electron precipitation on both the dusk side and midnight at high L shells. And to better understand the contributions of each scattering mechanism, we further analyze the energy spectrum as precipitation ratio. And on top shows you the median values. You can see that the precipitation ratio decreases steeply as the energy increases. But for the median value of the precipitation ratio greater than 300 keV are overtaken by the background values and greatly drops to 0. So in contrast, something interesting happens in the 90th percentile value and the mean value of the precipitation ratio. So for the slot region between L shell from 3 to 4, and also for L shell greater than 6, you can see that the precipitation ratio start off by decreasing at low energies and then increases as the energy increases. This happens on both on dusk, midnight, and dawn sectors. What is interesting here is that you can see those reversal points of the precipitation curve shows energy dispersion in L shells with higher energies at lower L shells. So these features are consistent with both the heat wave-driven electron precipitation in the slot region and also the current sheet scattering at higher L shells. And we can see that the highest spectrum is observed on the dusk side. And this feature is likely due to the relativistic electron precipitation driven by emic waves, which preferentially occur near the dusk sector. And this plot further shows the statistical energy spectrum of the precipitation events driven by emic waves. The left plot here shows the percentage of events with minimum resonant energy lower than a certain threshold for a given precipitation ratio. And you can see that for strong precipitation, with the start point of each line, only a small percentage of events shows precipitation at low energies. For example, for the events with minimum resonant energy less than 500 keV, the majority of the events have precipitation ratio less than 0.1. So in other words, the low energy electrons can be precipitation can be driven by emic waves, but it's much weaker than that at higher energies. And this can also be seen in the right plot, which displays the precipitation ratio as a function of energy, where you can see the precipitation ratio driven by emic waves increases monotonically with energy, with a precipitation ratio at around 0.5 at 1 MeV, but decreases to 0.1 at 200 keV. And this is consistent with the energy spectrum we observed on the dusk side. And we further explore the statistical energy spectrum under various geomagnetic conditions. And here, this plot shows you the energy spectrum under quiet conditions with AE index less than 100 nanotesla. You could see that the shape of the energy spectrum of the precipitation ratio is quite similar to the general conditions, where you see the dispersed reversal points in both the slot region and at higher L shells in the 90th percentile value and the mean value. And as the geomagnetic activity increases, is the moderate conditions, where you can see the reversal in the energy spectrum at L shell greater than 6 is primarily observed on the dusk side and dawn side. And for the midnight, it gradually disappeared. And as the geomagnetic activity continued to increase, the reversal in the energy spectrum at L shell greater than 6 is primarily observed on the dusk side. This is different from the general conditions or the quiet conditions, where we see this reversal in the precipitation, in the energy spectrum, the precipitation ratio, which has a broader coverage from the dawn and dusk and midnight sectors. And this is because the electron precipitation driven by chorus waves and current sheet scattering is enhanced in the midnight and dawn sectors. And also the current sheet driven electron precipitation would extend down to lower energies when the magnetic field lines are more stretched. So consequently, the reversal points in the midnight and dawn sector are no longer observed during these active conditions. And it's also, you can also see that during this active condition, there's no signature of heat wave-driven precipitation in this mean precipitation ratio. And this is consistent with our understanding that heat wave-driven precipitation has a larger spatial coverage during quiet times, and the plasmasphere is more compressed during active conditions. So that's pretty much about this work, and these are the conclusions where we focus on the 60 keV to 3 MeV electron precipitation, and we provide accurate measurement of the trapped precipitating backscattered flux, as well as the precipitation and backscattering ratios. We found that for 60 keV energetic electron precipitation, the precipitation ratio peaks from midnight to down to noon sector during active conditions, and this can be driven by both current sheet scattering and with-mode waves. And during intensive electron precipitation, only 10 to 20% precipitation are being backscattered. And this is consistent with model simulations. And for MEV energetic electron precipitation, they occur primarily from the dusk to midnight sector during enhanced geomagnetic activity, and they can be driven by both current sheet scattering and EMIC waves. And we also, by investigating the EMIC wave distribution, we show that EMIC waves mainly contribute to the dusk side energetic electron precipitation at L shell from 4 to 7 and midnight at L shell from 8 to 12. And the energy spectrum of the precipitation ratio shows reversal point, indicating the energy dispersion in L shells in both the slot region at L shell from 3 to 4 and also at higher L shells greater than 6. And this is consistent with heat wave and current sheet scattering respectively. And the highest spectrum of the precipitation ratio is observed on the dusk side. And those are likely driven by EMIC waves, which can scatter low energy electrons, but is more effective at scattering higher energy MEV electrons. That's it. Thanks for listening.
All right. Thank you for a wonderful talk, Murong. That was really interesting. It's really cool to see more observations from ELFIN. I had a quick question. For your statistics, have you looked at breaking them down by event as opposed to geomagnetic condition, say during the substorm expansion phase or recovery phase or during pressure pulses?
That's a good question. We were trying to do this, but the problem is that ELFIN has limited data coverage during last for 2 years. And sometimes the statistics, especially they've limited number of storm events, which allows us to study the electron precipitation during different storm phase or substorm phase. We were trying to do this and found some features during substorm phase, but for the storm phase analysis, I think the statistics is not enough for such kind of investigation.
Yeah. Okay. Cool. It would be really interesting to see the substorm stuff eventually.
Yeah.
That'd be really.
Yeah.
I think it would be. It seems to be a new way to look at it. That's a little bit different than just AE on its own.
Yes, yes. I hope the ELFIN mission could last longer, so it allows more storms to happen.
Yeah, absolutely. Okay, so we have no other questions today. So I want to thank you again for a really wonderful talk. Next week, we'll be following up with a talk from Catherine Davidson, and she'll be talking about investigating the dependence of high latitude thermospheric winds during or on geomagnetic conditions. So thank you again, Murong, and I hope everyone has a wonderful week.
Thanks, everyone. Thanks, Kyle.
Yeah, thank you.
Bye now.